strains and displacement at a much larger scale, at the basin scale. And many of those, not all of them, but many of those are called by tectonic plates movement in the far field. And because of that, these guys are called tectonic stresses. And epsilon 1,1 and epsilon 2,2 are called tectonic strains. If you know the value of those tectonic strains, you can compute what is sigma 1 and sigma 2,2. A few more things before we go to an example. There is a very important proportionality coefficient here. This one goes by E prime and is called the plane strain modulus. So the same way that before we found that the proportionality coefficient between strain and stress under confined conditions was the constraint modulus, now the proportionality coefficient for the tectonic strains is the plane strain modulus. And notice in the equation that if you apply a strain in direction 1, the plane strain multiplies that and it gives you the component of tectonic strain to add to this one. If you push in a direction perpendicular to 1, in direction 2, you have the same plane strain modulus, but now multiplied times the Poisson ratio. Which makes a lot of sense, right? Because the Poisson ratio, it tells this equation what is the proportion of that strain which is going to go into perpendicular direction, into direction 1. Remember, these two are horizontal. And it's exactly the same over here. You see inline stress and strain, plane strain modulus, perpendicular in horizontal direction, plane strain modulus times Poisson ratio, which is always a fraction of that strain. Anything else? I don't think so. So we can go to the example. And before we go to the example, this is the basis for what is called the construction of a one-dimensional mechanical Earth model. And for example, there are companies like Schlumberger that they are very supportive of these type of equations in order to model stresses as a function of depth. All right, so let's see an example of the application of these equations. For that, I have prepared an animation which is over here. Someone sleepy? And I know this is a time. This is not a very convenient time. Right after lunch, you know. Probably I'll bring coffee next time. Okay, so you will find this example over here. If you go to, so we're now here, okay. We're talking about linear elasticity, calculation of horizontal stress according linear elasticity. And if you go over here, these are the equations that we just worked out. Here you have demonstration. And if you go to this example over here, it will take you, not there, but it will take you over here. And I'm going to run this script. And here we're going to get the result of, let's see, what's going on. Didn't run. Let me try this. Why is this not working? Not trusted. Okay, let me reinitialize this one. What's going on here? Okay, let me try again. But basically, you know, what you have in this code is a set of tectonic strains, epsilon 1, epsilon 2. We have a Poisson ratio, gradient of vertical stress, gradient of pore pressure, and let's see if it works now. Okay, there we go. This will be, and you have the equations that we just wrote before are over here. Plane strain modulus EPS is over there. So EPS, you see, 1 minus Poisson ratio squared. And here we have total stress, vertical stress, pore pressure, and the horizontal stresses. Notice that there is a small difference here. Let me make this a little bigger. There is a, you can see here, if you guys can tell me how to change this, I appreciate very much. I looked for some time, I couldn't find how to set the precision of this number over here. It's not 0, okay? It's small, but it's not 0. And that's why S22 is bigger than S11, right? So if I were to apply a higher tectonic strain in direction 2, look how S22 changes. And if I apply a lot of tectonic strain, it can even go on top of the vertical stress. Notice that also S11 also changed, right? It also changed because of the Poisson ratio effect. It didn't stay at the same value. So this is a little bit slow. It's going to stop at some time. I think that's it. Let me decrease this somewhere over here. It's going to take some time. Let's just be patient. The next thing I want to do is, you can play with this later, you know, at home. And you have the script, everything there you can use for your homework. A very important thing here is that, and I didn't put emphasis so far, but you should remember very well, is that all these equations are based on effective stress, not on total stress, okay? So if you want to, usually our unknown, or what we want to calculate, is a total stress, not an effective stress. So if you want to calculate a total stress, you will have to add the pore pressure to that. But very important too is that, notice that here, that component, that contribution of the overburden depends on the pore pressure, depends on the effective vertical stress. So if I were to increase the pore pressure, also these are going to change, because now my effective stress, vertical stress changed, and so that the horizontal stresses also change. Let me add a little bit more pore pressure, something like that. Okay, now I have a very small vertical effective stress, and the other stresses are going to be proportional to that. There is something missing in this code that we're going to add later on. But we're going to see later on that linear elasticity is not enough sometimes to define stress. And there are going to be other limits for stress based on rock failure. And I don't have this in here, but I'm planning to add it later on. So these stresses are not going to grow forever, right? I'm going to put like a tectonic strain, say, of 10% and get this stress up here. It's not going to happen because before that the rock is going to break. And that's going to be something that we're going to see later on. So I encourage you to play with this code and see, what is the effect of pore pressure. Oh, we didn't change Poisson ratio, right? So look, Poisson ratio equal to 0, then I have no S11. It's the same as the pore pressure. So in order to have a lateral stress, I need some Poisson ratio. And the bigger the Poisson ratio, the bigger the stress in horizontal direction is going to be. Okay, good. Any question about this? No? I think you were raising your hand at some time. No? Yes.
I was trying to ask.
Or you were a little bit skeptical. Or
So,
yes.
What was my question? I had my question when we were talking about this difference between the static moduli and dynamic moduli.
Okay.
So the only way you can measure, well, not the only way, but usually the way you measure dynamic moduli is through like velocities, right? Sonic velocities.
Yes.
And you can only measure M and G directly.
Well, no, because you measure VP and VS.
Yes, and those directly translate to M and G.
Yes.
So you have to calculate both E and nu and everything through the relationships between them.
Yes.
And those relationships are only valid for linear, homogeneous, isotropic mediums.
Very well. Yes.
So how close are they to the real value if the medium is not isotropic, homogeneous?
Well, they can be quite far. Okay. The next step that you will go on doing this for an isotropic solid will be to consider transverse isotropy. And you can get similar equations, but instead of saying E static is equal to something times E dynamic, you will say Cij is equal to an F that depends on Ij. This will be static times the Cij dynamic. So for example, C11 static, which is the horizontal one, it will be a proportion of the C11 dynamic. And actually, my former student, Matt Ramos, and I have written a paper about that recently, so I'll be glad to share that with you if you want to know more about that. Yes?
So in case when you have something that's anisotropic like that,
Yeah.
Would you consider the Poisson ratio also changing?
So if here, it's a little bit...
Because that's the directional elastic modulus from what I understand.
So it's the Poisson ratio, it's a convenient number just for isotropic elasticity and to have an idea about how the rock deforms and have a physical meaning of that. Usually if you go into anisotropy, then you will have to do correlations of C11, let's say a TBI medium. You will have to do correlations for C11, for C33, for C13, for C12, and for C44, where these C13 and C12 and C44 already have the Poisson ratio in it. So now you have 5 independent coefficients. So they already have that influence of Poisson ratio there, and it's not necessarily assumed to be equal. All right, guys. Oh, by the way, I might not be able to make it next Tuesday. I'll let you know. I'll confirm. If I get on time here to Austin, we'll have lecture, but otherwise I'll let you know. So we have discussed so far these horizontal stresses for a homogeneous medium, but many times in nature we do not have a homogeneous medium, right? And most times we have layered rock formations, at least in the case of the subsurface. I ran out of paper. Anyone with no, but I don't like that paper. I want a paper without the ruling. Anyone? But a big one. No? Okay, don't worry. I'm gonna use the project. I'm gonna use this one. Oh no, okay, well I'm going to use what? But that's too small. I want one like this, okay? All right. Yeah. No, I'm going to use this one. Don't worry. So, okay. If you have a homogeneous medium, the equations that we use so far, they make sense, right? But what about if I now give you a stack of materials, of geomaterials, all of them with a given Poisson ratio and Young modulus? And I tell you to apply a stress on the sides, which is the same along that column. And let's forget a minute now, for now, about the weight of the rock. How is that deformed configuration going to look like?
Some layers are going to deform vertically more than others.
Vertically, let's forget a minute about the vertical deformation. I want to make a point for the horizontal deformation. What is going to be the horizontal deformation? And let's assume that each of those interfaces is frictionless. So I apply stress, which is the same here and there. It's going to be a function of the modulus, right? So the stiffer the modulus, the less the deformation. So for example, let's assume that this layer over here is very stiff. And so this is going to deform something like this. But let's say if I have a layer which is soft, it's going to be like that. But the point here is that it's going to depend. It's going to depend on what is the stiffness of the layer. Right? What about now if I told you that I get the same stack and instead of a constant stress, I prescribe very well a constant strain. All of them, I'm going to deform them exactly the same strain. What's going to happen?
The stiffer the material, the higher the horizontal stress.
So now the stress is not going to be constant anymore. Before it was constant. In this case, let's see, this was the stiffest layer, right? So it's going to look like this. And this one, let's say, was the lowest. And like that. Something like this. It's going to look something like this. This is going to be the horizontal stress. So these two cases are not the same, right? And with this equation over here, when we want to generalize this and apply it to a layer formation like this one, we're going to be closer to this assumption. Okay? It doesn't mean that it's perfect. And actually, it is sometimes it's not that great, but it's a good first approximation. But it makes sense that the stiffer the rock, the higher is going to be the buildup of stress if you have a tectonic strain, right? So this is the model that we're going to assume into the so-called 1D mechanical Earth model. So if, for example, let's consider that the influence of vertical stress here is very small, and most of the horizontal stress is given by tectonic strains. What would happen if, I'm going to just repeat this over here. So I have sigma h, and let's say that's the minimum principal stress, and my profile of stress, let's say, looks like this. Let me exaggerate a little bit more over here, where sigma h is the minimum principal stress, okay? If you try to do a hydraulic fracture at this location over here, what's going to happen with that hydraulic fracture? Let's say, these are all layers, and you have a very small, tiny hydraulic fracture which started to grow, and now it looks like this, coming out of the paper. And it's going to continue growing, all of these homogeneous, but then at some point it's going to reach the boundaries. What is going to happen at that moment?
It's going to stop.
Why?
You can't overcome the greater amount of stress once you.
Okay, but give me a little more detail. So which is greater, which is smaller?
So it's currently in the region that has the least amount of horizontal stress.
Okay.
It's the boundary. Now, for
Yeah.
you to expand, there's more horizontal stress that you need to overcome.
Here and there, right? So how is it going to grow? It's just going to stop?
Well, it's going to stop until it reaches a pressure in the fracture that's
Yeah.
greater than the horizontal stress. It's going to grow up first before it grows down. And then it's actually probably going to just continue growing up.
It's going to grow like in this direction, right? As long as the stress in this direction is smaller than some of those, it's just going to continue growing in this direction, just like a plane out of this. But notice that when these hydraulic fractures open, they need a width, right? And the bigger the width, the bigger the additional stress near the rock. So at some point, you may even modify this in situ original stress to be higher than this, and at some point you have a very fat fracture, that's going to be a lot of stress on the rock, and may get to this level so that at that point, continues and propagates through the other layers. So this one is going to continue propagating like a nice penny shape until some point over here, and when it reaches the layers, it's going to start to propagate just in that direction, perpendicular to the minimum principal stress. And this concept is the concept of vertical fracture barriers that are going to stop the hydraulic fracture to grow if you have a significant difference in the horizontal stress. For this case, we could also assume that, say, this is sigma h equal to sigma 3, and let's say this is sigma v. Otherwise, that fracture would not be perpendicular to the horizontal direction. And these same concepts are the ones that you have to apply for this project. So with density, with slowness, with the dynamic, and calculating the static, something I forgot about that. So here, in this equation, you have to use the static Young modulus and the static Poisson ratio, right? Because you're considering these are tectonic strains over a long time, sometimes involving a significant strain magnitude. So you have to use these two. And after you use those two, then you get sigma 11 and sigma 22. And once you get sigma 11 and sigma 22, you can determine, knowing pore pressure, you can determine S11 and S22. And you knew before what was SV or S33. And now you have everything you need. And that's basically it for this project. Notice that also here I have given you the value of tectonic strain. So you could say, well, what is the value of this tectonic strain? How do you know what that tectonic strain is? And actually, nobody knows that a priori. Okay, you could make a very rough estimation saying, oh, this tectonic plate moves 1 centimeter per year or something like that. But that's going to be not a very good estimation even if you do that. Usually these tectonic strains are calibrated with field observations. What does that mean? It means that sometimes, and actually this is in project number 1, you go to the field, you actually measure the minimum principal stress. Those are those red dots. The red dots in here is what is called a mini-frac test. So you actually go and measure it. You measure that stress because we don't know what those horizontal stresses are a priori. You measure those at different locations. You also measure what are the size of failures in a wellbore. We're going to see that later on, that the higher the horizontal stresses, the more failure you have around the wellbore, and also the orientation of those failures tell the orientation of horizontal stresses. But with these two together, now you can create your model, which the model here is the green and the blue curves, according to your field data. And you calibrate those tectonic strains. Actually, those are an unknown. But once you calibrate those, you can make an extrapolation of what the stresses would be at some other locations other than your measuring points. And this model and this paper that I'm showing right here is just a little bit more complex to what we have done, but it's exactly that. You have vertical stress, you have pore pressure. With that, you compute vertical effective stress. With two tectonic strains that are calibrated on field data, you compute SH min and SH max. And it's exactly what you're going to do in project number 3. We have 10 minutes. Any questions? No? Let me check if I have forgotten something here. Yeah, probably small concept that I didn't talk about. What is volumetric strain? We didn't talk about volumetric strain. Can somebody tell me what is volumetric strain? No. Or, so that's the way you calculate it, right? So where is our stress strain tensor? Okay, over here. So this is the strain tensor. I ran out of paper, so I'm just going to write it here. The volumetric strain is epsilon 11 plus epsilon 22 plus epsilon 33.
I1 of the strain tensor?
Yes, exactly. It's the first invariant of the strain tensor. And this is how you calculate it with the strain tensor, but the definition of the volumetric strain is a change in bulk volume divided the original bulk volume. So you can work through the equations and doing a geometrical analogy with a cube, and you will find out this derivation, which is in the notes I given you. And considering that I ran out of paper, I think we're going to stop here. All right. And on Tuesday we're going to talk about a general problem, a general solution, very general, for an elasticity problem, and we'll solve the Navier equations from scratch. But we're not going to solve them, but we're going to write them. Yeah. But we're gonna get to there, right? We're gonna demonstrate how we get to the Navier's equations and look at divergence of a tensor, a gradient of displacements, how we relate all of that to get to the Navier equations. All right, see you guys.